Alright, so in this video we're going to start our next unit, which is over waves and optics. And so in this video, in this unit we're going to be talking about obviously different types of waves. We'll be talking about properties of waves, wave behaviors, and some applications of wave behaviors as it pertains to sound and light, and which is basically what optics is. It's the study of light, essentially. The upcoming unit that we're about to start, it's not a hard unit. In fact, I would really say it's an easy unit, but there is a lot of information and detail that you have to know in the unit. This unit does not have a lot of equations, and I know I've said that before, but this unit literally has one equation in it, and it's a super easy equation. Okay, so all that to say, just make sure you're taking really good notes as you go through, write down the examples we do, anything else I say that sends out to you. Because like I said, there's going to be a lot of things where you don't have to do any math per se, but you need to be able to understand certain concepts to answer questions. Okay, so let's talk about what a wave is. So what is a wave? Okay, so we recently had a warm-up question where I asked you to draw a wave, and most people drew something kind of like this. Okay, if you ask most people to draw a wave, they might draw something like that. All right, so that is a type of a wave. So generally speaking, a wave is some type of repeating disturbance or movement that transfers energy, but not matter through space. Okay, now what does that mean, energy and not matter? Well, basically, what that means is that when you have a wave that's traveling, it looks like something is moving from, let's say, left to right or right to left. But what's actually happening is as the wave travels through something, let's say a water wave, the water is actually moving up and down and not necessarily side to side. And I have a video clip I want to show you guys to demonstrate that, and so I'm going to link that video. Pay close attention to the end of the video. It's a short video clip, it's like 2 minutes. Pay attention to the end of the video with the ball moving up and down in the water, and that's basically what I'm talking about when I say that a wave transfers energy but not matter through space. Okay, so that is the definition of a wave, and I will link that video. All right, so moving on, let's see. Waves transfer energy, not matter. I already talked about that. This is an example of a water wave formed by just like a pebble being tossed into like a pond or something. You can kind of see like the ripple pattern go outward from where the rock was tossed in. All right, so let's talk about different types of waves. And there's different ways to kind of classify and define waves. One way is by defining what's called a mechanical wave. All right, so what is a mechanical wave? A mechanical wave is a wave which requires a medium. So what does that mean? What do I mean by medium? So when we talk about medium a lot in this unit, and so when we talk about a medium is basically something that the wave travels through. So for example, if you have like an ocean wave or a water wave, the medium for a water wave is the water. Okay, if you're like watching this video in your room right now, the light going from your computer screen or from your phone to your eyeball is traveling through a medium. It's traveling through the air in the room. Okay, and so the medium is just whatever material the wave is actually traveling through. Could be water, could be glass, could be air, whatever. Now, there's some types of waves, like electromagnetic waves, like light rays, X-rays, all electromagnetic waves that do not require a medium, but mechanical waves do require a medium. And so that's basically the difference between mechanical waves and electromagnetic waves. Now, we're going to talk about a different way to classify waves. If I asked you to draw a wave, most people would draw something that looks like this, right? This type of wave that you see right here on the screen, this type of wave is what's called a transverse wave. And the reason most people would draw something that looks like this is because most waves are transverse waves. And so because it's a more common type of wave, That's what people are familiar with when they think of waves. In a transverse wave, the definition of a transverse wave is basically that the matter making up the wave is going to move up and down perpendicular. Perpendicular means at a right angle, at a 90-degree angle to the direction of the wave. Okay, so for example, if I ask you which way is this wave moving, most people would say the wave is moving from left to right. But if you actually look at the individual like dots making up the wave, the dots themselves, like look at this red dot right here. This red dot is moving up and down. So the wave is moving to the right, but the particles making up the wave are moving up and down at a 90-degree angle to the wave itself. Okay, so that is the definition of a transverse wave, where the particles making up the wave move perpendicular to, or at a 90-degree angle to, the direction of the wave. All right, most waves in the universe are transverse waves. Now, there's another type of wave, another type of mechanical wave, that is called a longitudinal wave. There's not a lot of examples of longitudinal waves out there. Let me give you the most common example. Okay, sound. Sound waves are longitudinal waves. So if you were to draw a sound wave, it would not look like this. It would look more like this. All right, so you might look at this animation and be like, what the heck am I looking at? So in a longitudinal wave, it still, it still meets the definition of a wave, but the particles making up the wave are moving back and forth parallel to the direction of the wave. So what I mean is here the wave is still moving from left to right, okay, but the particles making up the wave are also moving back and forth left to right. And so you can see some parts of the wave, like the particles, the black dots get like squished together, and some parts of the wave, like the black dots, are like spread apart. This is also called a compression wave because in a longitudinal wave, sometimes you get these areas called compressions. And again, the most common example of a longitudinal wave is sound wave. Most other waves are transverse waves. Sound waves are basically the only like common example of a longitudinal wave. And so when you're talking or when you hear my voice, what's happening is imagine these dots are the molecules in the air. And the molecules in the air basically move back and forth, just like you're seeing in this animation. And then when they hit your eardrum starts to move back and forth. And then your brain interprets that as sound. Right? So sound waves are longitudinal waves. Most other waves you can think of are transverse waves. So on this slide, we basically just have like, again, the two definitions of transverse and longitudinal wave. Here you can see like this is like somebody has taken like a big spring, like a slinky, and they've basically used it to make a transverse wave and a longitudinal wave, just so you can kind of see like the difference between the two. I'm going to link a short video clip just again to show you the difference between transverse and longitudinal waves. Obviously, you need to be able to like recognize the difference between the two and to draw them and give examples of different types of waves. Here again, you can see, longitudinal waves versus transverse waves. Okay, so what are some examples of longitudinal waves and transverse waves? Well, I already told you most waves that you think of are transverse waves, right? So what does that mean? So water waves, a water wave is a transverse wave. Like when you go to the ocean, you get hit by a wave from the ocean. That is a water wave. That is a transverse wave because the water goes up and down even though the wave is going sideways. A wave on a string is a transverse wave. So like if you play the guitar or the violin, if you pluck a string, the wave goes like down along the string, but the actual string itself like vibrates back and forth perpendicular to that motion. Okay, if you've ever seen somebody do the wave, like at baseball games, they do the wave where like they like stand up and they throw their arms up into the air. If you've ever seen the wave, that is an example of a transverse wave because the people are standing up and down. The wave is actually moving like sideways. Right, so the stuff making up the wave is moving perpendicular to the wave itself. And plus, any type of electromagnetic wave is a transverse wave. So light, microwaves, infrared, radio, ultraviolet, X-rays. All of those are transverse waves. Basically, the only example of a longitudinal wave is sound waves, and you can also use like a slinky to make a longitudinal wave, kind of like I showed you like back here. Okay, so that would be a longitudinal wave. All right, so there's different parts of a wave, and we're mainly going to look at transverse waves because most waves are transverse waves. Okay, so let's learn about labeling the parts of a transverse wave. Very simple. The top of a transverse wave is called the crest. The crest is the highest point on the transverse wave. The bottom of a transverse wave is called the trough, like what horses drink out of. Okay, the trough, that's the lowest point on a transverse wave. This middle line, this dotted line that goes sideways right here, that's called the rest position of the wave. Okay, and then finally there's two other parts. There's what's called the amplitude, which I don't know why amplitude is not shown on here. The amplitude is always measured from the rest position to the crest, or you could also go from the rest position to the trough. So it's this little bit right here is called the amplitude. I don't know why it's not in the notes right here, but that's the amplitude. And then finally, you have what's called the wavelength, which is literally just the length of the wave. Okay, that's measured horizontally side to side. Now, the way you actually measure wavelength is you pick one point on the wave, and you're going to keep going sideways until you get to that same point. So for example, if I start right here and I keep going sideways, I end up back at that point right here. And so that distance is the wavelength. Or you could also measure, from one crest to another crest. That's also the wavelength. Or you could also measure from one trough to the next trough. Okay, so it's just a horizontal distance where you pick like one point on the wave and you go horizontal until that point repeats itself. Whether it's crest to crest, trough to trough, or just like one random point to the next random point. Okay, so that's what's called wavelength. Now, for reasons I don't fully understand, wavelength has a special symbol in physics. For wavelength, we use the symbol lambda that looks like this. It is like an upside down looking Y looking thing. Okay, so that is the symbol for wavelength, and that's usually measured in like meters because it's a length. All right, so pause there if you need to look at that some more. And then just a few more definitions, and then we will be done. All right. Oh, and calculations. So what is wavelength? So we already kind of talked about what wavelength is. There's something that's kind of the opposite of wavelength, and that's called frequency. And frequency has a symbol lowercase f, just like wavelength has a symbol lambda. And so frequency is defined as the number of waves that pass through a point in 1 second. The unit for frequency is hertz. It's named after the guy that discovered radio waves. We write Hz for hertz. Okay, so that's basically how many waves per second are passing through a point. Wavelength and frequency are inversely related. Now, basically what that means is as one of them gets bigger, the other gets smaller. So for example, if you look at these waves down here, if you go from top to bottom, the wavelength is getting smaller because the distance between the crests is getting smaller if you go from top to bottom, right? So as you go from the top down, you get smaller wavelengths, but the frequency gets higher because you have more waves in the same amount of space. Okay, so higher frequency means lower wavelength and vice versa. All right, now here is the only equation you will see in this unit. This is called the wave equation. This is it for equations in this unit. Okay, the wave equation allows you to calculate the wave speed of a wave. Here is the wave equation. V is wave speed or wave velocity, whatever you want to call it. Wave speed, wave velocity. That's measured in meters per second, just like it has been all year. V is equal to lambda, remember that's the wavelength, times the frequency, that's F, that's measured in hertz. That is it. This is the only equation in this unit. This is the wave equation. Wave speed is equal to wavelength times frequency. Okay, so you're not going to have any crazy hard calculations to do in this unit. All right, but do make sure you pause here, write that down. Just because it's the only equation you're going to see, you got to make sure you get it down, right? Okay, so this is a wave equation, and then we're just going to take a look at some examples with the wave equation. So, example 1. Example 1 says a wave is measured to have a frequency of 60 hertz. Remember, Hz is hertz. So I'm going to label this F. By the way, random fact, but if you ever listen to the radio, like everyone has their own like favorite radio station. Like sometimes I'm in the car and I listen to like 106.1. Okay, so when you talk about a radio station and you say like 106.1, what that means, 106.1 is 106.1 megahertz. And so that number is not just like a random number for a radio station. That is actually the frequency that that radio station transmits at. Okay, so that's how you distinguish between different like radio stations. In case you didn't know what that number meant, that's the frequency of that particular radio station. All right, anyway, so back to this example. It says if the wavelength of the wave is 0.24 meters, calculate the wave speed. All right, so here's my wavelength. Notice it's in meters. Okay, so this is supposed to be really simple. V equals lambda times F. I'm looking for V. All right, I have lambda and I have F. V equals the wavelength 0.24 times the frequency of 60. I put that in my calculator. I get 14.4 meters per second. Boom. I'm done. No hard calculations with the wave equation. Pause there if you need to look at that some more. All right, example 2. Okay, it says a wave traveling with the speed of 150 meters per second is shown to the right. So now we have to be careful because now we have a picture that we're supposed to use. All right, so let's take a look at the picture. So first of all, we're given the wave speed in the problem. So we have V. The first question says find the wavelength. Now, in this case, we're not just like find the wavelength using an equation. We're using the picture and the graph to find the wavelength. So remember we talked about before, to find the wavelength, you pick one point on the wave. And in this case, it's at the rest position and it's going up. And you just keep going horizontally until that same point repeats itself. Okay, so I keep going until I get to right here. That length is the wavelength. So what length is that? Well, that's 8 meters because there's an 8 right there. So I would say from the graph, lambda, the wavelength, is equal to 8 meters. I know it's in meters because it says meters right there. The next question says calculate the frequency. So now I go and use the wave equation. V equals lambda times F. I go to plug in 150 equals 8 times F. I'm multiplying by 8, so I need to divide both sides by 8. Boop. I go to my calculator. I do 150 divided by 8, and I get 18.75 hertz. So Hz for hertz, and I'm done. Okay, so that is it for example 2. So pause it there if you need to look at that some more. All right, so we talked about amplitude before. I kind of showed you how you would find the amplitude, and you can also see from this picture. Something you need to know about amplitude, aside from like how to find it from a graph, is that amplitude has to do with the energy of a wave. All right, so it's very simple. Bigger amplitude means more energy. Okay, so frequency doesn't affect energy. Wavelength doesn't affect energy. Amplitude affects the energy of a wave. So like imagine like if you're listening to music and you turn up the volume. When you turn up the volume, basically what that means is you're increasing the amplitude of the sound wave. Okay, or let's say like you turn on the light and you have a dimmer, right? As you make the light brighter, you're basically increasing the amplitude of that wave, right? Because you're giving the wave more energy, right? So amplitude has to do with the energy in the wave. All right, so what you're seeing right here is basically just a picture of a longitudinal wave on a slinky. So longitudinal waves are a little bit different than transverse waves. They don't have crests and troughs, but we are going to talk about that um, at another time because I want to really focus on transverse waves right now because, like I said, most waves are transverse waves. Right? That picture we've seen before. Um, So I think we're going to go ahead and stop here. The other examples we can probably do in class just for extra practice, but you should at this point have enough knowledge to be able to do your practice assignment over waves. And so we talked a lot about in this video. Rewatch parts if you need to rewatch certain parts. But um, this unit is not super difficult. We've already seen like the one equation we have for this unit. You just have to know different things, right? So, as always, please let me know if you have any questions, and I'll see you guys in the next video.